Hello, my name is Aaron Balke, and in today's video I want to show off and go through my time series modeling assessment for my Masters of Data Analytics. This time series analysis is using a SRIMA, a S-R-I-M-A modeling method, and yeah, I'll just show it off. For this assessment, my research question is, using the provided data set, can we forecast out 6 months ahead? And the data set we were given was a set of revenue over time, and so there's just a quick little observed data graph right there. And so it's revenue for about 2 years, and I wanted to see if the last 6 months were able to forecast using the previous data. And I considered a good model to have a RMSE value of less than 5. 5 represents $5 million, so if we have an RMSE value less than 5, it would mean our model is accurate within $5 million on average. And with a time series model, the main assumption is stationarity. And so there can't be trends or seasonality within the data in order to have a mean, variance, and autocorrelation that are all time invariant. And so we require those to be decomposed from one another in order to accurately predict and fit future values. The other thing is autocorrelation. Autocorrelation is the coefficient of correlation between two values of a time series. And we want there not to be any autocorrelation because if there is, then that means that the residuals are not independent of each other. And we want either little or no autocorrelation to make sure that the residuals are not based on each other. And I like to think of residuals as just the randomness in the time series data. So the randomness can't be dependent on each other. For this analysis, we got the standard imports. We got pandas, numpy, pyplot. For the actual time series analysis, we are using stats models. That gives us the adfuller, the seasonal decomposing, the ARIMA modeling, and then the ACF and PACF objects as well. So those are the big main time series analysis Python objects we're going to be needing. We also are getting from sklearn the mean squared error in order to get the RMSE value for evaluation. And then at the end there, I do use AutoARIMA from the PMD ARIMA project module library because having the computer doing the ARIMA modeling makes it way easier and removes a lot of the work for me. So got that there. We do have the medical time series dataset import as well as a data frame. Once it is imported, the data frame, the next step is going to be preparing the time series data. The hardest part when it comes to time series data is getting the time to be accurate, like getting the date time values should be the correct format, getting them all to be the same as each other. Every time I've done time series analysis, this is where the problems have lasted, and you spend about 90% of your time getting this to work. And in order to get around this, I realized that the data just increments daily. Each day is a new value. And so all I did is I set up a start date, which was exactly the first date and in the format I wanted it to be. And then I just incremented by 1 for each day after that. And then I just set that to a new column and then deleted the original feature of the data set. So everything's in the format I want because I just create it from scratch and then just increment down that column. So that's what's happening here. The nice part about time series plotting with stats models and all is that if you set the date column to be the index, it automates a ton of the process. You don't have as much work you have to do to get to plot it in pyplot and all that good stuff. So we do set the date to be the index immediately. Then we got the time series, the observed data here, this is the revenue in millions USD over time. And so we're able to see that the theoretical hospital system has a couple months where it's losing money, and then it begins to have a massive increase, millions of dollars, and then we sit at, I'd say, roughly around 15 to 25,000 after the first year. So that's the observed data here. Time series data was provided as an incrementing day counter. Yep, so that was just me explaining what I had to do to get the dates to work properly. Next step is going to be checking for stationarity. As we mentioned in the assumption section, we need the time series data to be stationary. If it is not stationary, then we want to run a difference and a difference calculation on that data, on the revenue data in our situation. And when we do that, that will make it stationary by only keeping track of the differences day to day, as opposed to the original absolute values. We use the relative difference between each day. So we're running a Dickey-Fuller test to check for trends and to check for stationarity. If we have a p-value greater than our alpha value of 0.05, then that means that we're 95% sure our data is, if it's below that value, then we're 95% sure the data is stationary. If it's above that value, we are fairly certain it is not. And so if we run the Dickey-Fuller test here, we get back a observed stationarity, a p-value of 0.1997, which means we're fairly certain it is not stationary. So we do run a difference calculation on this to get the relative difference day to day of the revenue, as opposed to just using the absolute values. When it comes down to the auto-ARIMA and ARIMA modeling, we do just use the original data set, but put in that there is a difference calculation that needs to be done. That's just way simpler than trying to do this using this difference data frame at that point. Just be aware of that, but in this situation, we do remove we do apply a difference calculation to this data. For preparing the data, what we're going to need to do is we're going to need to get a training and a test split. The training and test split I gave it 6 months at the end. That matches our research question. It's also a nice even number when it comes to chopping up a year and time series data. We could have gone in here and done a exact 75-25% split. To be honest with you, I believe this is exactly 75-25% split. But what I really cared about was using a date that is rational, and so I did just use the midpoint of 2021. So everything June and prior is in the training set. Everything July and after is in the test set. And the nice part about time series data is we don't have to mess around with any sklearn training test split. We just are able to split it along the data frame using a string date value. And that is shown here. We're able to see the difference between the training and the test split. For the assessment, I was required to export the data, so that's what happened here. And on to the actual modeling and analysis. First thing we're going to want to do is just look at the data visually. I'm going to decompose the data using seasonal decomposing from stats models. And by doing that, we're splitting the time series data into 3 portions. We're splitting it into the seasonal portion. So what has a period to it, what has a cycle to it. We're splitting it into that portion. We're splitting it into the actual trend, which is how it goes up or down over time. And then the residuals, which are just sort of the random noise in the data set. So when we plot the seasonal component, we can definitely see there's something happening here. And in order to get the period of the seasonal component, we're going to use autocorrelation. And what we do is by applying autocorrelation to the seasonal component, we're able to get this plot. And with this plot, every time a day in our situation. Every time a day has a value, a correlation coefficient of 1, we know that's the start of a cycle. And so we're able to see that on the 0th day we have the start of a cycle, on the 7th day we have the start of a cycle, on the 14th day we have the start of a cycle. And so, since these are days we're counting, we're able to notice a weekly seasonal component to our data. So there's a weekly period of our seasonal component. The trend data, we're just pulling directly from the decomposition, and this appears to be what most of our data falls under. It's this component here because it pretty much follows the observed data as we saw earlier, just a little bit more smoothed out. I then did run autocorrelation and partial autocorrelation. The way of explaining this is if the autocorrelation tails off slowly, then we're able to tell that it is a AR model. If it cuts off all of a sudden, we're able to tell it's a MA model. And if it tails off, and we'll have to get the PCAF value, the partial autocorrelation as well. But if it tails off, it could also be the ARMA modeling method as well would be best. So we're able to see in our situation the data, the DF data. So this is the data with the difference applied to it already. We're able to see that does trail off slowly. So we're able to tell this is either an AR or ARMA model. And then we are able to see with the partial correlation on the difference data frame that it does just, I believe this just cuts off. Is this? I want to make sure here. Yes, cuts off at 1. And so we're able to tell that it must be a AR model because the partial autocorrelation cuts off and the autocorrelation tails off. I do have a little table up here to help out with figuring that all out. So tails and then cuts off. This means we have an AR model, so an AR model of 1, or another way of thinking about it is a ARIMA model of 1, 1, 0. The 1 value says it's an AR model, that's the P value. The next one is the amount of difference, so that's the D1 we already applied to make the data stationary, and then a 0 is the Q value. That would be if we had moving average MA modeling in there, but we don't since the partial autocorrelation cuts off at 1. So that's what we were doing here. For the assessment, I did have to also get the spectral density. To be completely honest with you, I am not comfortable and do not know what's happening in this graph. But spectral density, this shows the frequency, the cycles per day. This is something I need to get more comfortable with, to be honest with you. And then this is the decomposed time series data. One thing I did do that's a little bit special that isn't set up by default is the keeping the same y-axis for all of the components. And the reason I decided to do that was I wanted to show the magnitude of each component compared to each other. And so we did see earlier that there is a seasonal component here, but when you compare the magnitude of that seasonal component to the trends component or the residuals component, we're able to see that the seasonal component is very, very small and most likely not important for modeling our data. We're able to see, I believe when we look at the graph, yeah, it's 0.03 million USD that it's fluctuating between, which is very little in our situation. So that's the reason I have these set up here and why the seasonal component appears to be just a straight line. It's because when you compare it to the trends component and the residuals component, it is that small. And then we do plot the residuals as well. This is that little bit of randomness in the data in order to make sure there is not a trend or a seasonality in here, and there does not appear to be one. It looks like it just fluctuates around the 0 mark. So got that in here. And so that's it for our visual analysis on our decomposing of the seasonal trend and residual component. And the next thing we're going to do is use AutoArima in order to double check that our visual analysis was accurate. So when we ran autocorrelation and partial autocorrelation, we believed that our model was a AR model with a value of 1 and a difference of 1, or another way to say that would be a ARIMA model with a p-value of 1, a d-value of 1, and a q-value of 0. So no moving average, just the AR. But we do run AutoArima just to make sure that was accurate. And when we did that, we did get back that the best model was a ARIMA model 110. And then when I did put in the seasonal component that had a value of 7 days, which we saw from our seasonal component, it didn't come back with any values for that seasonal component. And the reason for that is because of how small that seasonal component was. As we saw, it's pretty much looks like a straight line when you compare it to the other values, the other components. So we do have the optimal model. It's the same model as we saw previously with the visual analysis and manual analysis. And this is a summary of the optimal ARIMA model. I did use the AIC values in order to compare the values. This was there was no reason for choosing AIC over BIC. It just was the first option, so that's what I went for. And so I then did set that model to be a different object. The reason for that is AutoArima sometimes gives out a weird object that's not as fun to mess around with. So I just remade the model in the standard ARIMA object. And so that's what we got here. And it should all be identical information as the AutoArima output. So that's what's happening here. And now with this model, it is time to do the actual forecast to see if we can forecast the last 6 months that match our test data accurately. So I run a forecast on the results of the created model to get a prediction. The start date is the end of the training data, and then the end date will be the length of the original data frame, because that should be the difference should be the test data set. So that's what's happening there. We run a mean forecast to get a forecast, and we get confidence intervals as well. I believe that was also something missing from AutoArima, was the confidence intervals, so that's why I did the separate object. And when it comes time to actually plot out the forecast, we can see it did something. What we got here, the blue data is the training data. The orange line here is the actual test data. The red one is the predicted one. And then this pink area is the 95% confidence area. So our model is able to say with 95% confidence that the revenue data will, the revenue in millions will sit within this pink area, but it believes this red line is where it's going to be. Now, as we can see, it doesn't really plot the changes and all of that sort of stuff. When it came to actually evaluating the model, we're able to see that the model fits the training data fairly well. We're able to see that the histogram, this is a normal distribution when it comes to the estimated density. We're able to see there isn't a trend in the residuals, and we're able to see it follows the normal QQ plot, the line, very well. But the the RMSE value, when we did make that the root mean squared error, it was under that required precision of less than $5 million. However, from the graph, we can see that the confidence intervals just expand astronomically as we go out to 6 months. When we're sitting at 6 months out, we can be anywhere from negative $10 million to plus $30 million. And so that is a very wide confidence ratio, a confidence interval. And the actual predicted value is pretty much just where it stopped, where it started predicting, and then it just went in a straight line. And so that is not particularly helpful either when it comes to predicting future revenue. If you just say, well, it's the current value, and just do that for the rest of the forecast. Just say we're going to make the same amount we made today as tomorrow will, as the day after will, as the day after will. So yes, we were able to say within on average, $5 million was our error. However, it's not very practical for predicting out, especially with this interval, the confidence interval being so wide. Now, the next question would be, why did this happen? And in messing around with the moving average value, with the different values that we could have had for our ARIMA model, it became clear that just having a very AR value of 1 and a D value of 1, then it is just going to give you a straight line. There isn't really much leeway in the terms of that. And so using a ARIMA model, this is the most accurate we can get with the current values we have, the training data. Something I did think about when it came to this analysis was we have the data from all the way back in the beginning of the hospital system, and so these values in the beginning, where it's sitting around a couple $1 million in the negatives, that isn't really something that you can use to save future revenue, because this was when the hospital system was getting started out. That's not really a accurate representation of the possible values that could be used to train the future plots and all. So something that I would recommend for this hospital system moving forward would be to cut off the first 6 months, since that's not really practical for predicting into the future, and get another 6 months worth of data and see if having just the data where the hospital system has finally got its footing and all, use that and see if we can make a more accurate prediction. Another thing that I would recommend is maybe using something other than a ARIMA model to predict and forecast future growth. The reason for this is for my I'm doing for my capstone project another time series analysis, and for that analysis I am running I'm using a data set that has a multi-seasonality to it, and ARIMA modeling just is completely unable to account for multiple seasonal components. And I'm wondering that may be a possibility in this situation where, yeah, we saw the 7-day seasonality. There is a chance that there's another seasonal component in here we missed because we're using a ARIMA model that's unable to take into account 2 seasonal components. So perhaps it was unable to keep track of that, and in turn gave a suboptimal model because ARIMAs can only do 1 seasonal component. That was something to keep in mind when it came to this analysis. And yeah, that's my time series analysis of this hospital data set. It was a ton of fun. I love time series analysis. I love the decomposing in particular is a ton of fun, and being able to see the seasonal components and all. So I hope you enjoyed this analysis, and yeah, have a good one. Thank you for watching.